Now let's see about finding the areas using integrals. As we know that one of the main applications of integrals is in finding the areas, the question comes on how we apply the process in finding the area using integrals. Say for example, I have my x-axis and my y-axis, and say this is the origin, and I have two curves, the one given by y equals f of x, and I have another curve given by y equals g of x. Now as I see these two curves, I clearly see that f of x is the upper curve and g of x is the curve which is below. So we say that f of x is the upper curve and g of x is the lower curve. When we see this, this is upwards and this is downwards, and therefore this implies f of x is always upper of g of x, that is f of x is always greater than or equal g of x, but here it is strictly greater than. So in this case, this being greater than this is the condition through which we are going to define area between the bounds. So for example, I want to find the area between x equal to a, where the line cuts at a and which is perpendicular to x-axis, and this is the line x equals b. Now using these two lines, we form a bound, that is we have to find area of this region. Now how do we find area of this region which has the upper curve f of x, the lower curve g of x, the left bound x equal to a and the right bound x equal to b, is what we connect with integrals. So this area can be found area of shaded region Therefore, area of shaded region is given by integral of the lower bound, which is x equal to a, and the upper bound, which is x equal to b on the rightmost. So integral of a to b, which is a definite integral of upper curve, comes always first, that is f of x, whatever is the upper curve comes first, minus the lower curve whole of dx, is how we define area of the shaded region using integrals, the definite integral. Integral lower limit to upper curve minus lower curve of dx is how we define the area of the shaded region. Now let's see the general formula. That is, in general, area under the curve or area between two curves or the area of this shaded region is memorized as area equals integral lower bound, and here comes upper bound, and here comes upper curve minus lower curve of dx, is how we memorize the formula for area between two curves using definite integrals. So generally for any curve, the general formula is derived as integral of lower bound, whichever lower bound is identified in the given problem, and the upper bound, and then the upper curve minus lower curve of dx. Now lower bound is always from left and upper bound is the rightmost. So here the leftmost boundary is x equal to a and the rightmost boundary for the area is x equal to b, and the upper curve is f of x and the lower curve is g of x. Is how we identify the formula for area of the shaded region or area under the curves using integrals. Now let's see some special cases of finding areas. As we have seen, the general formula now comes on the different special cases through which we understand finding the areas of various types of curves. Say for example, I have my x-axis and I have my y-axis, and here is origin, and then say I have the curve y equals f of x. I have only the curve y equal to f of x, and I have to find the area between the boundaries x equals a and x equals b. Is what we're going to find out here. So in order to find this shaded region, we have only one curve, but the formula is for two curves. But here, as we identify that x-axis can also be taken as a curve, as assumed that equation of x-axis is y equal to 0. That is, this area is between the curves f of x and 0. So if I assume these two curves, then again the upper curve is y equal to f of x and the lower curve is y equal to 0, and the left bound is x equal to a and the right bound is x equal to b. So therefore, area under the curve y is equal to f of x is given by integral of lower limit, which is a, or the lower bound, which is a, and the upper bound, which is b, and upper curve. Clearly in this case the upper curve is f of x, therefore I have the upper curve coming first, and then the lower curve is x-axis, that is y equal to 0, because the area touches till x-axis. Therefore the lower curve is 0 times of dx is how we get. So if you simplify this, that implies area under the curve denoted by a is integral a to b is how we get area under the curve. So area under the curve y is equal to f of x is this f of x dx is how we understand for only single curve. Now let's see the next case of finding the area. So for example, I have the x-axis, the y-axis, and the origin, which we have out here. Now suppose instead of the curve in the first quadrant, what if the curve is in the third quadrant, fourth quadrant? That is, I have the curve y equals f of x down in the fourth quadrant, and then I have the boundaries x equals a and x equals b in this form. So how do I find area of this dotted region? Using integrals. So this comes as a special case of finding the area using the general formula, integral lower bound to upper bound, upper curve minus lower curve of dx. So let's see finding the area of this case using the general formula. Now as we see that the area of required region is clearly with the general formula integral of lower bound. We know that the lower bound is x equal to a and the upper bound, which is x equal to b, and here comes upper curve minus lower curve. Now as I see this area, x-axis is the upper curve, which has the equation y equal to 0. So upper curve is x-axis and the lower curve is y equals f of x. So the upper curve is 0 minus the lower curve is f of x over dx is how the general formula reduces in the case of the curve in the fourth quadrant as seen in the diagram. Now when we simplify this further, I get this to be integral a to b of minus f of x dx. Therefore, the area is given by minus integral a to b f of x dx is how we understand the area in case of the fourth quadrant. The area reduces to negative value, and negative sign indicates only the direction of the curve, but the area is always positive. So this is how we identify the cases through using the general formula, and in case of this, area of the required region is minus integral a to b f of x dx. Now next, let's see the next case of finding the area. That is, if I have the x-axis and the y-axis and I have the curve y equals f of x, and I have to find area of this shaded region. Now I have x-axis, y-axis and the curve y equals f of x. Then how do I find area of the shaded region where the x-intercepts of the curve are given as a and b? So in this case, we don't have the lower and upper bounds given, but we have the x-intercepts which help us in finding the area. That is, if I draw a line perpendicular to x-axis, and if I draw a line here perpendicular to x-axis passing through b, then clearly I see that these two bounds are x equal to a and x equal to b as taken from the x-intercepts of the curve. So therefore, we have the bounds between which I have the curve and x-axis. Now as I see this clearly, my left bound is x equal to a and my right bound or the upper limit is x equal to b, and my upper curve is y equal to f of x, and my lower curve is x-axis, which is y equals 0. Therefore, area of required region is integral lower bound to upper bound of upper curve minus lower curve dx. That implies area is integral a to b f of x dx. Is how we identify the formula for area of the shaded region using the bounds, indirectly using the x-intercepts. Now let's take the combined case where two cases arise as different issues in solving this type of problem. Suppose I have my x-axis and my y-axis, and I have this with say my graph here has this as x equal to a x equal to b, and it has x-intercept as c. Now I want to find area of this complete shaded region. So how do I find area of this shaded region using areas of integrals, or the general formula is the biggest question out here. So as I see this, this has two different areas which are going to separately solve for and then add them to get the area this plus area this. So the idea behind is to find area of this, and when you add up, I get the area of the required region. So as I see this, I can see that there's an intercept C through which I can draw a line passing through and perpendicular. So clearly this line has the equation x equal to c because this line is parallel to y-axis. So I try to divide my region between these two bounds and these two bounds and then add up. So initially let this be denoted by area A1 and this be denoted by area A2. So I see clearly from the diagram that in order to find area A1, it is nothing but integral of lower limit, which is x equal to a, and my upper limit, which is x equal to c. And here in this case of my upper curve is y equals f of x and my lower curve is x-axis, which is y equals 0. So I have f of x minus 0 dx. That implies a1 is integral a to c f of x dx, which I take as equation 1. Similarly, let's find area A2. Now A2 is nothing but integral of lower limit, which is x equal to c, and the upper limit, which is x equal to b. So x equals c to b. Now in this case, the upper curve is x-axis and the lower curve is y is equal to f of x. So the upper curve, which is 0 minus f of x dx, that implies A2 is minus integral c to b f of x dx is what we get as equation 1 and equation 2. Now in order to find the total area, we add A1 and A2, then we get the overall answer. Therefore, adding equations 1 implies A1 plus A2 would be integral a to c f of x dx minus integral c to b f of x dx. Therefore, area is integral a to c to b is how we identify the area using integral concept. Now let's see the special case, the next special case, which is, suppose I have x-axis and y-axis and origin through which there are two curves. Suppose I have two curves where one of the curve is given by the equation y equals f of x and the other given by y equals g of x. Then how do we find the area of the region bounded by two curves here? So as I see in this case, clearly we do not have the left and the right bound, or the lower and the upper limit, but I have clearly the upper curve, which is f of x, and the lower curve, which is g of x. So in case of this kind of a problem, we have to find the left and right bound, or the lower and the upper limit. So how do we find here? These two is the biggest question. So as we know that if I have a line passing through the point of intersection of the two curves here and point of intersection of two curves here, we have 2 points of intersections, one given out here and the other given out here. So points of intersections of two curves will help us in deriving the lower and upper limits. So as I draw a line perpendicular to x-axis and passing through this point of intersection, and as I draw another line passing through this point of intersection, then the x coordinate of the point of intersection will be the lower limit. Say my x coordinate of this point of intersection is A and this is B. So it is very important to note that in case of this kind of a problem, the lower limit is x coordinate that is least of the point of intersection. So lower limit is x coordinate of the point of intersection, that is the least, and the upper limit is the x coordinate which is the highest of the point of intersection. So when we get 2 points of intersections, this is this and this, say I denote the point of intersection here as A and here as B, then the x coordinate of A will define the lower limit and the x coordinate of B will define the upper limit. Therefore, in order to extract the x coordinate of both the points, we are going to solve these two curves. The point of intersection A and B are obtained by solving the two curves y equal to f of x and y equal to g of x. So solving of two equations gives us this. Therefore, area is given by integral of a to b upper curve minus lower curve of dx. Is how we identify the areas between two curves whose limits are not given, but we find them using the point of intersection concept. X coordinates are the limits of the given integral, definite integral.